Okay, so this problem is asking you to solve for to list each of these light bulbs in order of brightness. And so the brightness is proportional to the power dissipated by a bulb. So we can solve for this answer by solving the circuit to determine the power of each light bulb. So you're going to find the total resistance first, since we need to find the current. So if you look at the circuit is actually just these two are in parallel, which is in series with this resistor. So what we're going to do is we're going to solve for the total resistance of this first. So the resistance of any resistor in parallel is going to be 1 over R total is equal to 1 over R1 plus 1 over R2. I'll name this R1, R2, and R3. So this is going to be 1 over 6 plus 1 over 12 is equal to 1 over RT. This is equal to 3/12. Since this is 1 over RT, this is going to turn into 12 over 3. So your R total for this part of the circuit is going to be 4 ohms. That's your total resistance of the parallel resistors. And then since we have the total resistance figured out for this part of the circuit, we're going to figure out the total resistance of the whole circuit. So the total resistance of the whole circuit is going to be, so the resistance in series is equal to R total of the parallel, I guess I'll name that RTP, plus R3, which is going to give us 10 plus 4, which is equal to 14 ohms. We can solve for the current. So we know that if we label this as A, B, C, and not just R1, R2, and R3, the current going through resistor A, or resistor R3, is going to be the total current that's flowing throughout the circuit, because according to Kirchhoff's joint rule, since these two make a joint over here, that's equal to the total current of here and here. Since that is your total resistance, you're going to do I is equal to EMF over R, which is equal to 42 volts over 14 ohms, which gives you 3 amps. So going on from here, power is equal to IV, which is equal to 42 volts times 3 amps, which will lead you to the answer of 90 watts. So this is for resistor A. Now for resistor B, this is going to be equal to the V, so I is equal to EMF over R. And we know that voltage is equal in parallel. You're going to get, this is, and since V is equal to I, we're going to do IA R, or resistance of the parallel, and then resistance of B. And so this is going to give you 3 times 4, as we figured out up here, over 12, since that's the resistor since that's the resistance of that resistor. So this is going to give you 1 amp. So if you solve for resistance over here, so P is equal to I squared R, which is equal to 1, square that, and get 12. So that's equal to 12 watts. Alright, so for resistor C, we're going to do the same thing that we did for resistor B. So I is equal to E over R, which is equal to I A R P over R A. This is going to give you 3 times 4 over 6. So this is equal to 2 amps. And if we continue from here, P is equal to I squared R, which is equal to 2. Square that times the resistance, which is 6. So you get 4 times 6, which is 24 watts. Alright, since brightness is proportional to the power dissipated by each light bulb, the one with the greatest power is going to be the brightest. So the order should be A with 90 watts, C, and B. And this is your final answer. Part B asks you to find the current through I, IV, and IC immediately after switch S is closed. You'll notice in this circuit that an inductor was added and a switch was added. So directly after the switch S is closed, because of the inductor's properties, there is no current that goes through this part of the circuit because it has so much back EMF. So this circuit consists of resistor A and B in series, and that's all that there is. I of C is equal to 0 because of the inductor, and so no current goes through this part. And so IA is equal to IB since they're now in series, which is not equal to 0. IA is equal to IB, which is equal to B over R. So this is equal to 42 over 10 plus 12, which gives you 1.91 amps. Part B, little 2i, asks you to find the current through A, B, and C a long time after the switch is closed. So because of an inductor's properties, a long time after the switch is closed, the potential across the inductor becomes 0 as the back EMF continues to get smaller and smaller. And so soon the inductor starts to act like a normal wire. So now you have this whole circuit just as it was before. Since the V across the inductor is equal to 0, your currents are basically the same as they were in part A. So IA is equal to 3 amps, IB is equal to 1 amp, and IC is equal to 2 amps. Part C asks you to graph function VL as a function of time across the inductor. So we know that according to an inductor's properties, it produces the most back EMF during its initial time period. So this specific time period, when switch S is closed, we know that the back EMF will be so great that it can't be 0 because it prevents any current from flowing through this half of the circuit. So we're going to start with a non-zero point on the graph. And you know that after a long time, the potential decreases to 0 because after a while this inductor starts acting like a normal wire. It gradually becomes 0, and the point of an inductor is to gradually decrease the current flow so that to make sure that there are no jumps. And so to gradually decrease it to 0, we're going to draw a concave upwards graph whose asymptote is 0. Okay, so part D replaces the inductor with a 5.0 microfarad capacitor. And so it asks you to sketch a graph of V across the capacitor as a function of time. At the beginning, when switch S is initially closed, we know that the voltage across the capacitor is 0 because no charge is stored on it yet. And so you're going to start at 0. And so from here, you know that as time increases, you're going to be going up to the total voltage. So the total voltage across the capacitor will end up being around 42 volts. So you know that this will be gradually increasing because as more and more charge collects on the capacitors, the more voltage it will have. So you're going to go increasingly upward, or decreasingly upward, because there's only a certain amount of voltage that this capacitor can hold. And so that's your answer.